Alright, we're going to begin section 14.8 in this video, which is change of variables in multiple integrals. So we've evaluated integrals using change of variables. We just haven't had to do the change of variables ourselves. So polar coordinates is a change of variables, cylindrical coordinates, spherical coordinates, all of those are change of variables. So now we're just going to go through the general technique of how to do set up a change of variables integral. So given, and I'm going to give the approach with a function, a double integral, but there's an analogous approach for a function, for triple integrals. So given an appropriate region R, so remember we use R in the XY plane and we use D when we're talking about our region in 3 dimensions, over which we cannot easily integrate. So for instance, it's neither a type 1 nor a type 2 region, or an integrand function f, which makes integration difficult. We may define a change of variables in order to evaluate the integral. Over a new region S. Suppose capital T is a transformation. And don't worry too much about the terminology transformation. We'll see when we do some examples more. So what I mean by this capital T, from, it's really it's just a function, but you don't have to worry too much about that. From S in the UV plane to R in the XY plane, given by X equals G1 of UV, Y equals G2 of UV. So we've seen this before. The way we've seen it is instead of UV plane, now we never sketch it, but if we said the R theta plane, if we were talking about polar coordinates, then X would be a function of R and theta. That function would be X equals R cosine theta. Y would be a function of R and theta. That function would be Y equals R sine theta. So we've seen a transformation like this before, but now we're just doing a general transformation. Then under the appropriate conditions, and stuff like that, that under the appropriate conditions, or earlier I mentioned the appropriate region R. The book specifies what those conditions are, but all of our problems will fall into those conditions. So I didn't feel the need for me to go through all of those details. The problems we do will all satisfy the conditions that we need them to satisfy. So under the appropriate conditions, the double integral over R of f of xy dA equals the double integral over S of f of g sub 1 of uv, because that's what our x is, comma g sub 2 of uv, because that's what our y is, and then times the absolute value of j of u comma v, and I'm going to define what this is, and then dA. And j of uv, that's what's called the Jacobian. So where j of uv called the Jacobian, also denoted with this partial notation, but it's still called the Jacobian, regardless of the notation you used. So you'll see it written like this quite often in your textbook. Is given by j of uv, or so whichever notation you want to use with the Jacobian, is equal to is 2 by 2 determinant the partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. And just in case we forgot how to compute a determinant, remember that's just going to be this times this minus that times that. So this is the partial of x with respect to u times the partial of y with respect to v minus the partial of y with respect to u times the partial of x with respect to v. And we've seen determinants when we were doing cross products earlier in the semester. All right, so I've done all this in terms of a function of two variables, and then in just a minute I'll give you the analog in a function of three variables. But one key thing before that, the book gives a good step-by-step approach for doing these problems, and we're going to follow that approach. So in using this change of variables approach. We will follow the procedure outlined on page 963 of your textbook. And then note there is an analog of this approach where f is a function of 3 variables. T is given by x equals g1, g sub 1 of u, v, and w. Y equals g sub 2 of u, v, and w. Z equals g sub 3 of u, v, and w. And the Jacobian of u, v, and w is the 3x3 determinant. Oops. Missing the indeterminate on page 967. Alright, so I'm going to stop this video here, and then in the next video we're going to start with exercise 24 from this section.